So let's begin with section 8.1. All of these problems can be solved using integration by substitution. So let me write that. Section 8.1, integration by substitution. Now this is often called U substitution. Simply because U is typically the symbol that's used to denote the new variable in the integral. Because what it really is it's a change of variables. In the integral. And you're starting with an old variable, the original variable, which is typically x, or sometimes t. And you're changing to a new variable, which is a function of the old variable, u of x, or maybe of t, depending on what the old variable is. Now, of course, you could call the new variable something else if you wanted to. You could call it v, w, whatever, etc. But it's typically called u. And so the whole name of the game in this context is to choose your u, to look at the integral and figure out, well, what choice of u will make the integral simpler than it was before? So let's look at the first one. So this is number 16. I'm going to rewrite it here first. Integral of 5 over t plus 6 cubed dt. In this case, a good choice of u is t plus 6, in which case du is just dt. Now this still confuses some people, so let me spell out what we're really doing here. You remember we're choosing a new variable, which is a function of the old variable, and so the u is really u of t, and this is the form of that function. It's just t plus 6. Then you differentiate the function. You know how to do that. You write du dt equals, well, in this case it's just 1, because that's t to the first power, and that's just a constant. Now you imagine you take this expression here, rewrite it here where there's a little bit more room, du dt equals 1. Now if the du and the dt were algebraic quantities, if they were actually actual numbers or something, then what you could do is you could write a dt over on this side and a dt over on this side, multiply both sides by dt, and then these would cancel and you'd be left with your du equals dt, which is what I've written here. Now this operation here is not really valid because, of course, the du dt is not a ratio of two algebraic quantities. The du and the dt aren't really individual quantities. This thing is really a limit. You remember du dt. It's a limit of ratios of quantities. So this is a limit as a delta t goes to 0 of a delta u over delta t. That's one way of defining the derivative. But even though this isn't really valid, it works in this case. And so we always do it, because what it does is it leads to a valid expression. When we take the du and put it into the integral, then it becomes valid in that context. So it's almost like two wrongs making a right. In any case, it's what we do and it works. So this is all commentary. We don't need it. We've decided what our u is, we found what our du is, and now we can substitute. So we write the integral as integral 5 over u cubed du. If you like, you can rewrite this pulling out the 5, and you can write the u as a negative exponent here. Now you can use the general power law for integration, which says the integral of u to the n du equals, well, it's u to the n plus 1 over n plus 1 plus the constant of integration. Now this is the case if, so this is true if n is not equal to minus 1. Of course, if n is equal to minus 1, then you're just getting integral of 1 over u du, and you know that that's ln of the absolute value of u plus c. But in this case here, the exponent is not equal to minus 1, so we can just use this expression here, which I'm sure you remember. And once again, all this was just commentary. We don't really need it. And so we can then proceed to write this is equal to 5 times u to the minus 2 now divided by minus 2 plus c, because that's increased the exponent by 1, divide by the new exponent. I can simplify this by pulling the minus sign out, writing 5 over 2u squared, moving the negative exponent in the numerator down to a positive exponent in the denominator, plus my constant of integration, and then this is just 5 over 2, and I substitute back in what the t was. And see, the reason why I do that is because we originally had an expression in terms of t. We want to end with an expression in terms of t as well, and that's the answer. So the reason I chose u equals t plus 6 here is because it simplifies things. It makes essentially the part from the 6 goes away, and I'm just left with a variable that's raised to a power here. One thing to remember in general is that you can make any substitution you like. I mean, you can define a new variable any way you like. It's just that it might not help. So there's not always one way that's necessarily the only way to do it. It's just that you want to make a good choice. Let's do the second one. This is 22. So this is integral x plus 1. Now this time x, the original variable, is being called x. 3x squared plus 6x under a radical in the denominator here, dx. Now a good choice of u in this case is u equals 3x squared plus 6x. In which case, I don't know if I may have room to write it there, so I'll write it down here. du equals 6x plus 6 quantity dx. Now remember what I've done here. Again, I'm going to write this and then I'll erase it. I'm defining u as a function of x, and that tells you what the function is. It's 3x squared plus 6x. I'm differentiating it. Du dx equals, well, it's 3 times 2x to the 1. That's just the power law here, plus 6, and then this is times x to the 0, because that was just x to the 1. And so this is just 6x plus 6. I could recopy this here, du dx. And then I'm thinking of multiplying both sides of this by dx. The dx is canceled here. I'm left with the du equals this thing, which is what I wrote there. So this is kind of the intuitive reasoning of what's behind that expression there. Now, the reason this expression here is going to be useful is a little bit less clear than it was in the last one we did, because in that case the du is just equal to the dt, and so we could substitute it in directly. What I'm going to do here is I'm going to write another step where I'm going to factor out the 6, and then I'm going to have an x plus 1 dx. Now the reason I'm doing that is because this x plus 1 dx is what I actually have inside the integral. See, I have inside the integral x plus 1 dx. That's what I want to substitute for. See, now I can substitute because I have something, this part here, I can substitute in for that under the radical. And then this part here, I can put in for there in terms of du. Now, it would probably even be useful to write, if I wanted to, go into excruciating detail, I can write another step. I can write 1/6 du equals x plus 1 dx, because then I have exactly what I have in the integral here, and I can substitute it in precisely without having any additional factors. So now I have two things. I have this expression, which is what appears under the radical there. I can put the u in for that. I have this expression, x plus 1 dx, in the numerator, and I can put this in for that. So I can write this thing equals integral of, well, what's in the numerator is going to be 1/6 du. That's just the x plus 1 dx. What's in the denominator is going to be just square root of u. Let me draw a line here. So I can factor out the 1/6, and then I can write this as the integral of u to the minus 1/2 du. That's just changing this to a fractional exponent and then moving it to the denominator. Because, I mean, if I was going to write, well, I mean, I guess I could write an extra step. The extra step would be to first write this as 1 over u to the 1/2 du, and then I would write 1/6, and I move this up to the numerator as a negative exponent, negative 1/2 du here. Now this is once again, this is the power law of integration, where I have u to the n du, and it's not minus 1, the exponent isn't minus 1, so it's just u to the n plus 1 over n plus 1 plus c. So what that gives me then is this gives me 1/6 times, well, what happened with this? I have u now to the 1/2, because that's minus 1/2 plus 1. All that's divided by 1/2, and then this is plus the constant of integration c, and I can erase this part because that was just commentary. So let me divide this here and then this here. And now we can simplify this. So this is 1/3 u to the 1/2 plus c. And then finally we put in the original variable again. So this is 1/3 3x squared plus 6x to the 1/2 plus c. And if you like, you can rewrite it again under the radical. You can replace the fractional exponent with a radical if you want to. I forgot to put the x there. 6x plus c, and that will be the answer. Now, the reason this one worked out fairly easily is because it was essentially a contrived problem. I mean, the people who wrote the book, they made it to where the thing you chose for u, when you differentiated it, it would spit out something exactly that was proportional to what was left in the integrand there that would give you your du. So you can't take it for granted that all substitution problems will be this easy, but this one worked out fairly nicely. Okay, let's move on to the next one. So this is number 32. Now this one looks awful at first glance. Cosecant squared x, e raised to the cotangent x dx. Now, in this case, you have to choose. The only reasonable choice is going to be u equals cotangent x. Now, how would you know that? Well, you know if you have e to something inside an integral. I mean, you know, for instance, that integral e to the u du is just e to the u plus c. So that's a reasonably easy integral to do. It's a very easy integral to do. And furthermore, you know, if you have some kind of complicated expression, like, you know, if you have e to the x squared dx, for example, then you're going to be in trouble. So the only way you're going to be able to integrate this easily is if you have an e to the u here, and then you had better hope that the du is going to give you something that will simplify the rest of it, which it will in this case. This is almost using psychology to solve this, so let me just make this remark. So this is almost using psychology of textbook makers, and that is for calculus. And what that psychology is that no one will buy my book if it has hard integrals in it. So, which is true. I mean, no integral you encounter in this elementary calculus context is going to be a very difficult integral. So if it doesn't simplify in some magical way, then it wouldn't be in the textbook. So it must simplify in a magical way, and it does. So what happens? Well, I choose u equals cotangent x. Now du then is going to be minus cosecant squared x dx. That you may not remember. It's a derivative of a trigonometric function. If you didn't remember it, you could work it out easily as follows. You have, so I write u of x equals cotangent x. What is cotangent? It's 1 over tangent x. Tangent x is sine over cosine, so another way you can write this as cosine x over sine x, and then you could differentiate it. You can write du dx equals, well, it's low d high, so this is sine x, derivative of the top there is going to be a minus sine x because it's coming from cosine, minus high d low, so this is cosine x, derivative of that is another cosine x, and then this is over the bottom squared, which is sine squared x, and so I get a minus sine squared x minus cosine squared x over sine squared x, and that is minus sine squared x plus cosine squared x over sine squared x. This is just doing every single possible step. Well, this thing in here is 1. You remember that, right? That's from your friendliest little Pythagorean theorem where the hypotenuse is 1. Then this side over here is sine x, if that angle is x. This side over here is cosine x. That's your favorite little trig identity. This is minus 1 over sine squared x. Well, 1 over sine x is by definition cosecant x, and so this is exactly minus cosecant squared x. And so you see it took me about a minute. If I had forgotten, it took me about a minute to work out what it was. You're not helpless in that context. You can get it, you can dig it out if you forgot. But that's all commentary. We don't really need that. We have the u, we have the du. And now we can proceed to substitute. Now if I wanted to, I could write an extra step here, which is negative du equals cosecant squared x dx. And the reason why is because what I actually have in the integral is a cosecant squared x and a dx here. And this is what I want to take this thing and put it in. I want to take the du and put it in for that. So now I have something to put in for the cotangent, something to put in for what's left. So I can proceed to write this as integral of, if I put in this part first, that's just e to the u, and then what's left is just minus du. So this is minus integral e to the u du. You know what that is. It's minus e to the u plus the constant of integration, and then I can substitute back in what u was, and this is cotangent x plus the constant of integration, and that's the answer. So you see it was actually quite a simple problem, simpler than the last one. This one here, even though it looks really quite ugly. You just had to choose a good x, remember how to differentiate it, put this stuff in, and it works out magically. Okay, let's do the next one. So this is number 40. I'll copy it as I did with the previous one. 25 plus 4x squared dx. Now in this case, you're not going to know what to do unless you can remember some standard integrals. The integral you want to think of in this context looks like something like this. I'll use a variable w just because I don't want to commit to calling it u, because I'm going to call u something there. Now this is the integral that gives you the inverse tangent. So this would be inverse tangent w plus the constant of integration. Now the reason you think about this is because you have something that looks quite similar to it in here. It's just that it's multiplied by different constants. So what you want to do is you want to mess around with the x or the u or whatever in order to make it to where the size of this 25 is going to be the same as the size of whatever multiplies the variable here. And then you can pull it out as 1 over 25 and you'll be left with a 1 plus the variable in the denominator there. And then you can use this formula. So that's what your reasoning would be to start with. Now the choice that will actually do that for you would be u equals 2 over 5x. In which case, of course, du is just 2 over 5 dx. Now, you have in here an x, and you want to substitute in for that. So what you can actually invert this if you want to. You can invert these expressions, and so you can write x equals 5 over 2u. And then you can write dx equals 5 over 2 du. And that will give you things you can substitute in, because now I can put in, I have an x squared here, so I can put in this expression for the x, and then I can put in this expression for the dx. Now, if this confuses you, you can rewind it and watch it and go over it as slowly as you like, but I'm just going to proceed. So that lets you rewrite the integral as integral of, so I have 1 over 25, and then I have, let me fix this here, plus 4. Now what do I have inside here? Well, I told you x is 5 over 2u, so I get a 5 over 2u, and then that whole thing is squared, and then the dx, which goes out in front, this is just going to be a 5 over 2 du. So now let's proceed to simplify. I'm going to pull that 5 over 2 there out in front. Now what happens here? Well, this is a 25 plus the 4 is here, and I'm going to square this. So I'm going to get a 25u squared over 4. Because the 5 squared to give a 25, the u squared to give a u squared, what else would it be? The 2 squared to give a 4 here. And then I'm left with a du at the end of it. Okay, so to proceed, I have a 5 over 2 coming out here, down here. Now, so the whole reason I chose this was, like I said, to make the size of this number here the same as the size of the coefficient of whatever the new variable is going to be in here. And you see, so the 4's will cancel there, and I'll be left with what I want. This is 25 plus 25u squared du. I can write an extra step, I guess, which would be to write this as 1 over 25, and then this is 1 over 1 plus u squared du. And now let's see if I can make room to finish this here. So the 1 over 25 comes out. So that's going to give me a 5 over 2 times 25. That's a 5 over 50, which is 1 over 10. This is going to be 1 over 10 integral of 1 over 1 plus u squared du. So this is all inside here. And now I have that form that I wanted that involves the inverse tangent. So this is going to be, I have to write it down here because I don't have enough room otherwise. This is 1 over 10 inverse tangent of u plus c. Now I want to put back in what the u is. And I chose the u to be 2 over 5x, so this is 1 over 10 inverse tangent of 2 over 5x plus c, and that's the answer. So this one hinged on beginning with the end in mind, knowing a form, namely this one that would give you the inverse tangent, that you want to convert it to. Now, if you don't know how to do that, if you don't have, in your brain a library of a whole bunch of integrals and stuff, well, you do in your book, or you do online or something like that. So if you come to an integral where you're like scratching your head and you're thinking, I'm not quite sure what to try to convert that to, you don't have to just sit there in futility. You can go find a table of integrals and think, well, this kind of looks like one of these on here. What do I want to convert it to? Now, of course, you'll find tables of integrals that will actually tell you, it will have like it will replace this thing in general with a 1 over like a squared plus b squared x squared or something. And then it will give you that form there directly from it. But of course, you would still have to show, what your steps are, but at least it would tell you where you expect it to go. Or you could put it into a symbolic manipulator and get it to tell you what the answer is, and then you would have to try to go and work backwards and figure out how to show that that was the answer. Okay, so there's one more in section 8.1, and this is number 46. So let's do 46. Rewrite it here. Integral 1 over x squared minus 4x plus 9. Now this will involve, I think, a little bit more algebra than the previous ones have. The first thing I'm going to do is I'm going to complete the square in the denominator. I'm thinking essentially along the same lines as I was in the previous one. In other words, I'm thinking about something that looks kind of like this. And I want to eventually get an inverse tangent. And the way I want to do that is I want to complete the square in here. And then I'm going to have something squared plus a constant. And then I'll change that something squared to be my new variable. We'll see how this works out here. So I'm going to say first complete the square. Now the way this looks is I can rewrite x squared minus 4x plus 9 as x squared minus 4x plus 4 plus 5. Now the reason I've done that is because then this is equal to x minus 2 quantity squared plus 5. And you can go back and multiply that out and spend as long as you want on convincing yourself that that's actually right. Now, when I get that, I'm taking the integral now down here. Now it's convenient to write this as that expression, x minus 2 squared plus 5 down here dx. Now it's at this point that I want to make my u substitution, so let me draw a line across here. And so I will choose u equals x minus 2, in which case du is just equal to dx. And then I'll put this in as integral of now 1 over, this is just u squared plus 5 du. Now I'm in a similar situation to the way I was before, in the sense that this kind of looks like my u squared plus 1, which is what I would want if I'm going to use inverse tangent. But it's not quite that way because there's a 5 here instead of a 1. So I want to choose a new variable, so I'm going to do another substitution. I'm going to choose w equals, let's see, 1 over square root of 5 times u. Now, why do I choose this? Well, watch what happens. So another way I could write this, so I could say that I could either write it that way, or I could say, or u equals square root of 5 times w. I could write it either way I like. Now, if I write it this way, then what I'm going to get is du equals square root of 5 dw. And then watch what happens when I substitute this in. I'm going to take, this would be integral 1 over, now what I'm going to have here, I have u squared, so that's square root of 5 times w, all that quantity squared plus 5. And then what comes out in front, the du becomes the square root of 5 dw. Okay, so let's persevere. This becomes integral of, now watch what happens down here. The square root of 5 turns into 5. The w turns into w squared because I'm squaring it. So I'm getting 5w squared plus 5. And then this square root of 5 I will leave there, dw. Okay, let's see if I have enough room to finish here. I can pull out a 5 here, and I can pull out a square root of 5 here. So this is going to come out to be square root of 5 over 5, integral of 1 over w squared plus 1 dw. I think before I wrote this as a 1 plus w squared in the denominator, but it's not going to make any difference. So now I can perform the integral. This is square root of 5 over 5, inverse tangent of w plus c. And now I have to go back through and remind myself what w was in terms of the original variable. And I think I'll have to come up here in order to do it. This is where I have a little bit of room left. I guess I can do one more step down here. So this is going to be square root of 5 over 5, inverse tangent of, well, first I can rewrite w, I can replace w with u. See, I had w equals 1 over square root of 5u, so that's the first thing I can do. I can write 1 over square root of 5u there plus c. And then finally I can go back and look at what u was. U was x minus 2. So what my answer is going to be finally at the end of the day is square root of 5 over 5, inverse tangent, x minus 2 over square root of 5 plus c. And that's the answer. So that one was a little bit more involved, and it involved, the way I chose to do it involved 2 substitutions. See, if you were clever, if you were sufficiently clever, you could just make a single substitution. You could go straight from x to w, but that would involve being able to see all the way through the problem to see that this would be the best choice for w, x minus 2 over square root of 5. And that's probably too much to ask, so it's better to just do it in 2 steps like this, I think. Okay, so that's the 8.1 problems, and I think I'll break the video here just because just so it won't be too big, and then we'll go on to do the 8.2 problems.